All the model engineers are screaming at their YouTube right now. What the James is she doing? She's gonna jam up that parting blade and shatter it. This is a disaster. Is it? And if so, why? Stay tuned to find out. Hello Internet, my name is Quinn and this is Blondihacks. You know that age-old game, if you were a piece of a steam engine, what piece would you be? Well, people have trouble figuring me out and nobody quite knows what direction I'm going to go in, but I always get there in the end. So I think that makes me the eccentric. Well, the eccentric is kind of like the camshaft of a steam engine, and we're going to make one right now. Here's our starting point. I've got a bronze casting for the clamp and some steel for the hub. So the hub fits inside the clamp. I guess we have to do a little more work on these parts yet. I'll start by cleaning up the casting, as is tradition on this project. Got little mold lines there running down all the surfaces. When filing a curve, remember you always want to actually describe the reverse arc with the file that you're trying to create on the part. I'm going to set it up to drill out the clamping bolt areas first, and there's no references on this thing yet, so I'm just kind of squaring it up on the sides of the casting as best I can. You'll note that I left the sprue on the top there. I think that's going to be useful for fixturing later, so I didn't want to take that off yet. And now these bolts just need to be kind of aesthetically centered, so I blued them up and just measured the center with calipers, and I just eyeballed the center drill on there, and that seems like it's good. And the other sanity check I can do here is to bring down a drill the same size as the clearance holes that we're ultimately going to be drilling and make sure that they line up on the curved edge of the casting there the same way that they do in the drawing, and that looks good. So now I can center drill this hole, and then I'm going to drill all the way through with the tapping size. These are 540 bolts that hold the two halves of the clamp together. The basic idea is we have to pick the exact right moment to split this casting into the two halves that form the clamp. So we do everything that we can before cutting the thing in half so that we've got the alignment established with the clamping bolts. So that's why we're drilling and tapping these holes now while it's still all one piece. So we drill tapping size all the way through because there's threads in the bottom half of the clamp, and then we got to come in and drill the top half out to clearance size for the top half of the clamp. So I do that by bringing the drill down to touching the part, and then I zero it out, and now I can measure depth from there. There's a little bit of inaccuracy in this because of the drill cone interacting with the center drill there, but that's okay, it's close enough for this. Now I can come in with the 540 tap, which will pass through the clearance hole and thread the bottom half of the hole. Little test fit here with a 540 bolt, and that threads in there nice, so I think this is going to work. Now the bolt heads do interact with the curve of the casting a little bit, and so the drawing calls for a spot face here. I decided it was easier just to mill a flat spot here, so what I did is I just milled inwards from the edge until there was clearance for the bolt holes against the curved part of the casting there, and this was just a trial and error process. But once I had a fitment that I liked, I looked at where I was on the DRO. It tells me I'm 30 thou off from where the hole was because I'm using the incremental scale for one hole and the absolute scale for the other, so I could easily just move over to -30 on the other scale, and I'll have the same size spot face on both sides. And you could argue that I should have done the spot face before the drilling, but until you've drilled, it's hard to know how much clearance the bolt head needs because you don't know exactly where it's going to land. Now for the valve rod mounting point, so I milled the top flat. The drawing calls for this to be machined flat, though I don't know that that's actually necessary, but I did it anyway. Now the mounting hole here is strictly aesthetic because the valve rod is going to get bent into position anyway, but I just blued it up and centered it as best I could by eye using a center drill, and then tapping size and tapped 540. Now interestingly, the drawing specifies this to be tapped all the way through. I would think that's not actually a very good idea because all that's going to do is risk impacting the hub that's spinning inside with the valve rod, but that's what the drawing said to do, and I don't know enough about the situation to second guess it here, so I went ahead and did it that way. And after a little deburr and cleaning out with some squeezy air, the valve rod fits in there good, so I think we are good to go on that one. Now I'm flipping it over sideways and I'm using the machined top of the valve rod mounting point there to get the oil cup mounting boss facing upwards. I machined the top of this flat, though the drawing didn't actually say to do that, but there's going to be an oil cup screwed on there, and I thought a machined surface would seal better. Now we're going to need a way to bore out the center and face the sides of this thing. We could try to hold it in the forejaw like that. You might get away with that, but I didn't feel very good about it. So I decided to make a fixture to hold this thing in the lathe. So I found a piece of scrap aluminum here, and I'm just milling the top of it flat. And then I did a lap around the outside to square up the sides. The actual dimensions here don't matter as long as it's big enough to hold the part. This is a quick and easy way to square up a block in certain situations. It works best if you've got a lot of extra material on one side of the block, and on the hobby mill it really only works in soft materials because you do need to do a lot of milling on the final side. If you had to do this in steel, you'd be here all day doing this, so you're better off starting with a block that's close to final dimension and using the traditional one side at a time method of squaring that I've shown before. After the sides are milled and deburred, then you can flip it over and then just mill off the excess on the top there. You could certainly leave less excess there than I did as well, but this was the parallels that I happen to have, and so I just milled this down, and this is aluminum, so it doesn't take too long. I also drilled and tapped a couple of holes for this little piece of scrap that I found in the junk bin that happened to be a good size for this, and I'm going to use it as the side of my fixture. Then I threaded a transfer screw into the casting there and used it to scribe the correct height for a mounting bolt on the side. And then I could come back in and lower the area where that little block is going to sit, and by creating a gap there it's going to create a clamping effect. So then I can drill a clearance hole through that little block, and you can see how this is all going to work. So that screw is going to clamp into the side of the casting, and that way it's going to create all vertical clamping force. All the clamping is going to be in the same direction, and that'll keep the part nice and flat against the fixture there. You can see how that little gap that we milled is going to create the clamping force as needed. Then on the other end we can drill through that sprue that we left, and that's going to clamp the other side. But before I can drill out that tab, I have to split it first because it's going to get shorter. Now I have to clamp it all the way on one side of the vise here, which is a little sketchy. So I've got a drill bit and a shim, which together are a little thinner than the casting, and so that'll clamp squarely, keep the vise jaw square. And then I'm going to bring the slitting saw down, find the top with a feeler gauge, and then find the bottom with the same feeler gauge. Then use the half function on the Z-axis on the DRO, which I don't think I've ever done before, to get the exact center of that cast boss there. And make sure to spray WD-40 on the saw so that you get soaked when the saw starts. That's really important. And now we can make our cut. As I always say with slitting saws, it's best to do full depth cut all in one pass, because that way the saw is clearing chips efficiently and you're engaging as many teeth as possible, because these saws always have a lot of run out in them. I find these operations a little terrifying, but also very, very cool. I actually really like slitting saws. Because it was sitting on the machined boss at the bottom there, we can just flip it 180 and it will repeat the same height that we had, and we can just leave the saw right where it was and cut the other side, and it'll come out the same height rather precisely. And this is a little bit down to how good the castings are on the side, because we're squaring up against the casting each time, but this actually turns out quite well. These castings are very good. And now for today's dose of precision porn. Open the vise and click. Because the surfaces were cut with a slitting saw and they're sitting on a machined boss, the clamp simply collapses onto its own surfaces. This was not expected, but extremely satisfying. Yoink. Villains, I shrieked, dissemble no more. I admit the deed. Tear up the planks. Here, here. It is the beating of his hideous heart. Now the casting is supplied with extra oblongarity, let's say, so that you can have varying amounts of saw kerf and still have room to make it round. So now we have to measure it in both directions and see how much to mill off of the faces of the clamp surfaces. But for some reason I decided to drill the other side of the clamping fixture here first. So I drilled a hole in the middle to allow me to clamp the casting, which would then allow me to go over and drill out the tab there for mounting this end. So I milled a flat spot and then drilled a clearance hole all the way through the casting there, and then I tapped the fixture underneath, and now I can clamp both sides of the fixture in place. However, this is going to come back to bite me later, as you'll see. However, a little test fit of the clamping action there on both ends, and that looks good. So back now to the clamping surfaces. So I'm going to square those up using a square, and I can get away with this because I cut these with the slitting saw, so I actually know that they're very parallel to the casting. So I'm just milling half of the amount that I calculated needed to come out for making the casting round. So now I'll check here how we did. So we're within a few thousandths of being round, which for a casting is pretty darn good. And it's a good sign that the clamping bolts came out flush, so I guess I did something right there. What I did not do so right, however, is I drilled that hole before milling the excess material off of the clamps, so now the holes don't line up. Luckily, it's an easy fix. I can just put some washers in behind the other end to shift it over and get the holes to line up. But I thought that was a funny little brain fart. We should have everything we need now to bore out the center of the clamp. So I'm going to set it up in the lathe with some parallels to get my fixture block square to the back of the chuck there. Now I chose to dial in the center of the casting because that's what I'm going to bore out, but it would really be better to dial in the outside because that's what you want to look aesthetically centered when you're done. The center bore, the casting might not be perfect, but it doesn't matter because you're going to bore it out. However, there really isn't a way to do that because of how little room there is exposed on the outside of the casting. So I dialed in the center, but I haven't had any trouble with these castings being out of concentric. They've been good so far. And then also put an indicator on the front of the casting just to make sure it was reasonably square with the machine so that I wasn't having to machine off too much of the faces. And now we're all set to start boring. And I made the fixture out of aluminum so that I can dig into it a bit with the boring bar on the back side of the bore here, and it's not going to hurt anything. And it's also worth noting that there's actually quite a bit of extra material on this casting. They're pretty generous with this one, so we don't have to worry too much about getting things perfectly square and true when we set it up. So I'll give a little check here and see how we're doing. So we've got a little ways to go yet. So I think that should be it. I'll get out the bore gauge here and see how we did. We're aiming for 1 inch nominal. I think we can go a little bit over that. And we are at, well, would you look at that? Even a blind squirrel nails a dimension sometimes. Now, without touching anything in my setup, I'm just going to use the boring bar to face off this side of the clamp, and that should ensure that it's very, very square to the bore. This is the same trick that I learned from Keith Appleton for facing cylinders. Works great for eccentric clamps as well. This particular style of eccentric is sitting in a groove in the eccentric hub, so it's actually very important that the bore and the sides be extremely square to each other to run smoothly in that groove. Now I gotta check the thickness here. What we're trying to do here is machine the same amount off both sides so that the cast features around the outside land roughly centered aesthetically on the clamp. So I'd measured the casting before we started and figured out how much I needed to remove off both sides and end up with the casting features centered. And the nice thing about this fixture is that I can remove the clamp and then just flip it over and put the now machined surface up against the face of the fixture, not move anything, and the clamp on the right side there, the little bar, is adjustable for the now lower face that's been machined, and then I can just machine this side the same amount to get it down to the final thickness. And because the casting is sitting on a machined surface on the machined fixture, I can just measure the depth from those two surfaces to find out when I'm at the right thickness. Now this fixture doesn't repeat concentrically, so you can see run out in the bore there, but it doesn't matter because we're just facing. Because the machined surface on the other side is up against the fixture, we're going to end up with the outsides of the clamp parallel and also both square to the bore, all of which is what's important. And so we just machine this down to the final depth, and that's looking good. So this quick and dirty little fixture did its job. That's looking pretty good so far. I forgot to chamfer the corners, unfortunately, so I'll do that by hand on the bench, but a little quick check and see how we did on parallelism. It looks like we're within a few tenths here, which is down to how good or bad my fixture was. And so now I'll just deburr those. And now I think we're finally done with this little tab, so I will cut this guy off with the Dremel and then file it flat. It was just kind of a gut feeling that maybe I should leave that tab in place, and I'm sure glad I did, because I'm not sure how I would have fixtured this thing without that, honestly. And finally, something I probably should have done sooner, I punch marked the two halves so I know how they go back together. In the hobby shop, things are never made perfectly, so it's always a good idea to put things back the same way that they were when you made them. On to the hub now with this piece of steel, which you may recognize from such videos as Steam Engine Piston featuring Quinducky. The kit comes with enough of this to make the piston and then make the hub while still holding onto it with the chuck, but it's pretty close, so don't get sloppy when making the piston or you won't have enough of this stuff left for the hub. So I'm going to face this off, as is tradition. And then square up the tool post using method number 58 that I have for squaring the tool post, which is to use the work. Just using my scale here to line up the edge of the tool with the face of the work there, I can now set up an indicator and move the grooving tool over to line up with the groove that we need to cut. Now the groove is wider than my grooving tool, so I'm going into one side of the groove that we're going to need. I'm going in and leaving a couple of thou extra on the diameter so we can finish the entire groove in one operation down to final size at the end. My indicator is still set on the carriage, so I can use that to move precisely to the far edge of this slot, subtracting the width of my parting tool, which I happen to know. And then I can plunge in on this side as well, and I'll end up with my groove exactly the right width. And once again, I'm going into a few thou short of final dimension, and then I go all the way into the final dimension and then move across. And this is a grooving tool, but you can turn laterally with it as long as you're only taking off a very small cut, and that ensures that the groove has a nice smooth surface inside. And I'll deburr that, and I did actually leave the final dimension about 1 thou large just so that I A, don't overshoot it, and B, have room to polish it up. I want to make sure that the finish in there is really, really good. To double check the width of the slot there, I've got some gauge blocks ringed together for the correct width, and if I did my indicator math right, that should be a really nice slip fit in there, which it is. That's a perfect snug fit. So I think we got the dimension right there. That's important so that the hub will move smoothly in there. Now, a quick test fit with the hub, and I wouldn't expect it to fit yet because we're still about 1 thou large. And you can see that it's close, but there's a little tiny gap there. So we know we've got a little bit more to remove out of there. But width-wise, it feels really good, so I think we got that part right. So now I'm going to go in with some cutting fluid and a little strip of emery paper, and I'm going to polish it up and bring it down that last little bit. The width, depth, and surface finish of this groove are all really important for that eccentric clamp to spin really smoothly here, so I'm taking my time and trying to get this really, really right. So as I was polishing, I was doing some test fitting, and after a few iterations of that, I got it to where that fits on there really nice, and it's important to test this with the screws all the way tight because that clamp will tighten up more than you think just by holding it by hand. And that spins on there really, really nice, but there's no play in it, so I'm very happy with that. And now I need to offset this thing to turn the eccentric portion that makes it into an eccentric. Now, quick sidebar here, because there's a couple of really good ways to do this, and then I'll show you how I did it at the end. One is to turn a fixture that will hold the part off center, which you can do by just turning a blank and then drilling a hole off center that's the right size for your part. You can also lay out the center of your eccentric area, center punch it, and then put a dead center in there between centers and dial in the dead center. I'll link to my video called Stupid 4-Jaw Chuck Tricks where I demonstrate this technique to dial in an eccentric. What I'm going to do though is I'm going to use the indicator. So if you're careful, if you can lock the chuck, do it. If you can't, just be careful not to move it too much, but you can put an indicator on there and just shift the part laterally in the 4-jaw chuck the amount that you want for the offset of your eccentric. This is not the most precise method because it's easy to accidentally turn the chuck while you're doing this, but if you're careful you'll get it close, and this will get us within a few thou, which is plenty precise for the slide valve on a model steam engine. Eccentric turning is really, really cool. It looks crazy when you start, and when you first start making passes, you're convinced that all you're doing is ruining this part. Like, this can't possibly be the right thing for you to be doing with a lathe. It looks crazy, but the more you cut, the less and less crazy it looks, because as you start to get into more and more solid material, as you can see here, it starts to look like a spinning part concentric with the machine that just happens to be off-center with the stock. So as you can see here, the more we turn, the more sense it makes. And then once we get to the point where we have a full cut around, then it really starts to make sense. So that's starting to look like an eccentric now. We still have quite a bit to go down there with the diameter. At least we don't feel crazy anymore. Well, not for this reason anyway. And then at the end of the day, this is really just a basic turning to a shoulder operation, except the base of the stock is sort of like a virtual part that's the diameter of the maximum swing of the eccentric. So you have to face a long way out as you face off that shoulder, much further than you would expect, because of course the swing of the eccentric all has to be covered. Now we can put a little chamfer on that, and now we can drill for the hole where the crankshaft goes through, because of course the part that we're creating now is actually the non-eccentric part, if you will. The part that we made earlier was actually the part that swings around off center. So I center drilled, pilot drilled, drill this a little bit undersize, and then I'll ream this to final size for the crankshaft. So it's looking good, but I'm not going to try to part this off yet. I'm going to leave the material on there because I want to take it over to the mill and take advantage of that material to hold it in a collet block and drill and tap the hole for the grub screw that attaches this to the crankshaft. To position this hole in the X, it was easy to edge find, but on the Y, the edge finder wouldn't fit. The boss is too short, so I used this old school trick of pinning a thin parallel with the drill until it's level, and then I was able to get in there with the center drill. You might be asking, how on earth did I not hit some part of that fixture? Well, as machinists like to say, clearance is clearance. And the reason for center drilling that is because I can come in with the tapping drill size and it's not going to wander off the crest of that convex surface now. Finish up with the tap, and the grub screw is complete, so now we can go back to the lathe and prepare to part this off. So now I'm dialing it back in on the first diameter that we used, which is actually the eccentric diameter. I started parting this off when I realized there's a few other things I need to do actually on this diameter while I have it, one of which is chamfer a couple of the corners. And I'm also emery papering the outside because you may have noticed I never turned the OD overall, and that's because the stock that they supply is actually the same diameter as the expected nominal for the outer diameter of the hub. So I just left it unturned and I just polished it up with some emery paper, and that is sufficient. I'm parting it off with extra material on the inside there so we can face it off to final dimensions so that the rim there is the right thickness. If you're experienced with making eccentrics, then you might be cringing right now because you know that it's actually dangerous to use the parting tool with an eccentric hole in the part. Because what happens is when the parting blade breaks through that hole, the top surface of that hole is going to swing around and bang into the top of the parting blade, and it's dangerous. It's going to bind up or break the blade. But I don't go all the way through. I just go in until I start to touch that hole, and then I use the slot that I've made to go over and guide the bandsaw through nice and clean without damaging the part. And there's my saw cut there. So I'll freeze it here and show you what I mean. As this rotates around, you can see how the top of the arc of the hole, once exposed, suddenly becomes a cliff that's coming down on top of the parting blade. So that's what you don't want to happen. But I wanted to use the parting blade to give me that slot so that I could do a nice clean bandsaw cut and not risk drifting off into my part, which would have been very sad. So now I'm going to set it up in the forge jaw the other way, and it's kind of difficult to hold now because it's got the groove in the middle. So I've got these scraps of copper round bar, and I filed one side of each one flat so that they'll sit on the groove there, and then I can clamp it in and I can dial it in. Now I can't put parallels behind like I would normally do because of the eccentric hub, so I'm just getting it square to the machine using an indicator, and I can just tap in the high side and indicate and tap in and indicate until it runs flat all the way around on the face, and then I know that it's square. And now it's an easy job to face off that saw cut, and then I can face this rim or this lip of the hub down to the proper thickness. And you'll notice that it's not running super true there. I couldn't really dial in the hub concentric. There wasn't really anything to put an indicator on, but it doesn't matter because we're just facing the back side off here. We don't need it to be running concentric. Okay, that's looking good. I think this part might be done. Yep, a little bit of deburring here on the bench. And that is the final hub. It's looking pretty decent. This was actually a really fun part to make. It's pretty simple, but had some fun operations in it. All right, let's put this assembly together. So I've got some assembly oil there on all the parts, and put the two halves of the clamp on there. And then screw the clamp together, going back and forth to clamp it evenly because it's a very close fit. And that should spin freely on there, which it does. Now onto the engine, so that slides onto the crankshaft and snug up the grub screw, and you want it not touching the casting because that casting surface is not machined, which kind of seems like maybe it should be, but the drawing didn't call for it. That spins freely, and then the eccentric will move freely as such. And here it is in action with the valve control rod that you haven't seen me make yet. So just pretend you're not seeing that, but I wanted to show you the eccentric in action so you can see how it works on the crankshaft. I think these look really cool because it kind of looks like the hub isn't spinning. I don't know why, but I find them sort of magical looking. Anyway, I hope you enjoyed watching me make these. If you like these videos, maybe throw me some love on Patreon. Thank you for watching, and I'll see you next time.